The next challenge I thought I would take on in my Zynq build is to start doing programmable logic-based graphics drawing, and starting really simple, I guess, with primitives, things like rectangles, circles, lines, polygons, whatever they might be. And step one of that for me, I'm picking to do a rectangle. So can I draw rectangles from programmable logic, in other words, from Verilog, in my specific scenario? And can I control that from PetaLinux? So from PetaLinux, can I initiate the request to draw from Verilog in the programmable logic side of my system? So that's what I'm going to do in this video, is kind of walk through maybe a start to a framework that I could use. I have no idea if this is a good way, bad way, or what other options are out there, but this is what I've come up with so far. So definitely would be curious if any of you have done stuff like this, where you're trying to basically manipulate video memory from programmable logic, be able to integrate that or initiate that from let's say some C application in Linux of some form. But again, for my setup, I'm using PetaLinux, I'm writing applications in C, and then I'm using Verilog on the programmable logic side. So maybe here's a real quick block diagram of what I'm essentially at what I've set up and am trying to work with. And it's been a while since I posted. This has been a little bit of a slow process. I'm in no hurry. I'm just kind of working through this and learning as I go. And like I said, if you've got suggestions, definitely drop a note below in the video. To the left, I've got my Vivado block diagram, Verilog, just simply saying I have my Zynq processing system, and to build that, I'm using Vivado, and in that I have a block diagram. That block diagram, I'm using some different IP blocks along with some Verilog that I have put together. And I'll talk through those pieces here. And then, of course, I have PetaLinux. So for my system, I'm building a PetaLinux image. I boot to that PetaLinux. And I'm, as part of that, running, for now, an application called FB Test that I wrote. And that really started out as a frame buffer test program, and I just keep adding a little bit of functionality to it to test some of this other stuff that I'm doing. So step one, and I've had this in my system for a while, I've got a video buffer. So basically in memory, in DDR, in the RAM, I have some range set aside to really represent the video output. And so I'm using a frame buffer read. This is one of Xilinx IP blocks that I'm using to read from that video buffer. And then I have the rest of my system set up to output that as HDMI 1. And if you're interested in more in the details of that, you can check out previous videos that I posted on that. I then have a second set of that for HDMI 2. And I did remove the VGA support for now. I also have a VGA output on my system, but for this specific video, I'm not using it at all. Now beyond that, then over in PetaLinux, these two HDMIs will show up as FB0 and FB1 in the devices. So I've got dev FB0, which is this first frame buffer read. So if I manipulate that frame buffer directly, using whatever form I want to use to modify a frame buffer from PetaLinux, that of course will output on HDMI 1. Same with FB1, we'll go to HDMI 2. Then I have, in addition to this little FB test I've written, inside of that previously I've shown things like little animated sprites move across the screen, or color bars that drop down the screen. That was all C code that was manipulating FB0 and FB1. And in a previous video, I even did it across 3 screens. So HDMI 1, HDMI 2, and VGA. And really, I'm just accessing those through a frame buffer device. But now what I'm going to do is do something a little bit different. And maybe even before I mention that, I can use also just a direct modify memory from PetaLinux using things like devmem. So I can use devmem, I can go out to one of these video buffer areas, write to it, write the color data directly to it, and that'll also work. And I'm sure there's a slew of other ways to write to memory, but that was another simple test way I was doing it for a little bit. But what I want to do now is really come up with something different, which is to be able to do manipulation of the video buffer from programmable logic. And so I put together a graphics controller. This is in Verilog, and that graphics controller then has basically other modules that it can call. And I'm starting out with just a rectangle one. So I've got a rectangle one for this video, and in the future, I'm hoping I can have circle, line, maybe get to polygon or other things like that. Now, this GFX controller will generate really the data using the rectangle module. And then it's got to get it to the video buffer. And I'm doing that through an AXI memory writer that I put together, also programmable logic. So I have a GFX controller. It leverages this rectangle. The rectangle module helps it generate the pixel data for whatever I'm trying to generate. And then I write it out through an AXI memory writer. And then to control it, I have some GPIOs set up in the block diagram, the block design. And from my C program now, this FB test, I can call or write to those GPIOs basically that allow me then to control the GFX controller, such as setting the width and height of the screen, setting the start location, end location of a rectangle, telling it what color I want to fill it, and then also actually basically flipping a bit that says, okay, do it, kind of a start type of a rising edge case. So that's what I've been working through and trying to get this all working. And I know it still looks like a lot on the screen, and it took a bit to kind of work through those pieces, get all of this, I'd say just skeleton set up and at least the basic rectangle working. So with that, maybe what I'll do is I'll jump out and walk through this. So if you're interested in seeing this run, I'll do that first, and then I'll go back through all the details. I'll walk through my block diagram. I'll quickly pull up the programmable logic that I have, this Verilog code, and maybe the C application, just so you can kind of see what it is that I'm working with here. So I'm going to get out of this here, and a couple of things I'll pull up before I get too far. I have OBS running, and I'm going to use these three screens that I have. One is just a live video capture of my board. So this is the same board I've been using. This is my primary HDMI output, this one right up here. That is the one that is going to show Wayland, Weston Wayland when it boots up. And then this one up here is my secondary HDMI, and that's the one that is going to be used for this testing I'm doing. I'm writing to the memory address for that second HDMI from both, I guess, C code using the frame buffer, and then also from programmable logic. I'm trying to leave this main display just as my primary video output, and this one is the one that I'm experimenting with. And then this VGA I mentioned I'm not using in this video. And then you also see this box up here I now have added into my setup, and I'll talk more about that later, what the purpose of that is, maybe towards the end of this video. So that is my board, and then I have two windows down here. This one is showing the output of my primary display, which has probably gone to sleep now. So let me just move my mouse on my, this is the mouse on my little PetaLinux build here. So this is Zynq board. This is the mouse on my host that I'm recording this on. But this is running, this user interface here. Again, this is this, oh, sorry, actually I said Wayland Weston, but this is Matchbox. So I can run Weston from here, but this is actually Matchbox. So this is the main UI I run when I boot my system now. It's lightweight, it seems to work great. And actually inside of here, I'll just be able to open up a terminal and do things in that terminal. And I can have multiple terminals open and do a bunch of stuff with that. So I could use that as I need to here. And it looks like I actually have a couple of terminals open already. So I'm going to close those just to get them out of here. The other video output then is my secondary screen, secondary HDMI. And this is a previous color bar test that I have these float down from the top portion of the screen down. And that's just what I have sitting here right now. And I'll come back to that. So live webcam, HDMI 1 output, HDMI 2 output. If I get over to maybe testing this, what I'll do, I think I'll make this output a little bit larger so we can see what is being output, and then this I will make larger, and I think I might even just, let me get back into a terminal here. Oops, wrong mouse. And that might even be hard to see. Maybe let me just jump out to a console and see if that's a little bit easier to work with. Okay, so there I just have a console that I can use if I want to use that from my primary output, and that's using the keyboard and mouse for, again, my Zynq board. Something else I guess I do also have open is just a good old terminal session opened up going to the same board. So whether I use this down here or I use this up here, it'll be the same effect. And actually this one's maybe easier to read at this screen resolution, so I'll maybe use that just to get going here. But I have this tool, so FB test is what I put together, and these are the things it can do right now. So it can do listing out my my frame buffer device information. So if I just say show config, and then I tell it which frame buffer. Now this will be FB1. It's my second frame buffer is this screen over here that I'll be working with. I can then see at what memory address does it start. Of course, I can convert that back into hex. I can come on down here and see it's a 1280 by 720, and it has a virtual Y vertical resolution of 1440, meaning that I've got two frames in this frame buffer that I can switch between if I choose to do so. And I do have all that support working at this point, so I can write to one frame that's not active, switch it to the active frame, write on the other now non-active frame, etc. And I can maybe point that out when I get into my C code. But other things that I might do besides show config, I've got an RGB bar moving test that I showed previously. This in previous videos that uses the frame buffer. I've redone that same thing that uses programmable logic with a little bit of control from C code. I've got animated sprites, display full screen image, which actually right now the image I'm using as a test image is for a different resolution, so it doesn't quite look right. I've done a triple display test recently where I have bars move across from screen 1 to 2 to 3 just to show that I can treat them all as one large canvas. And then I've got a couple new, and I'm going to focus on these two down here right now. There's a programmable logic graphics controller test. And then I also have one that does a bunch of just random rectangles. So this first one I'm going to run, I'm just going to say FB test, and I'm going to do a test 5. And then when I run that, what you'll see on my output, which I noticed quit capturing, I have an actual monitor also hooked up here. So let me get back to OBS and see. OBS sometimes does not do well with keeping video capture devices working. Okay, I had to reset my video capture device and get OBS to be happy with it again. But going back to this is the output. And maybe what I will do just to back up a step, I'm going to run FB test 1, which is just this floating bars that go from top to bottom, and that blanks the screen as part of it. So I'll do that, and I'll write that out to FB1. And so there's that test, and then I'll go run this test 5 again. And when I run this test 5, it is going to draw these shapes. So I've got this, you can't quite tell, but there's the corner that starts at the very corner of the display with this small white box, and then I just build up these other boxes. And what I'm doing that with is what I was showing over in that previous slide. really using this application FBTest to write to some GPIO that then uses a graphics controller that I have in programmable logic. And that graphics controller draws the white box, and then I make a call to draw the red box, the green box, the blue box, etc. And maybe what I can also show is this FB test 6. What I'm going to do in this one is just randomly draw boxes within a certain size on the screen and just have it do it as fast as it can. And so you'll see that this can actually draw this content quite quickly. And what's happening here is from C in PetaLinux, from that application, I'm generating a random start position, a random end position that's within a certain size, so no larger than a certain size of a rectangle, and randomly place it, pick a random color, draw it, and then move on to the next one. And I don't know how well this will capture, in the OBS recording, but it's moving along pretty quickly. It's drawing these rectangles quite quickly for this little system. And really, what's happening is the processor side of things here. So my processing system, the lift that it's taking on is the calculation of random data and making these GPIO calls essentially, or updates to GPIO data. And then all of the drawing of the content is happening from within the actual programmable logic within the Verilog modules that I have. And I can make this bigger just so you can see it for a second, but you can see that just as kind of flying through this content. But what I'm going to do now is just break out of that. And I'll go back and walk through some of this content here in my block design. So I have my block design opened up, and let me show you the pieces that I am using to make this work. So of course I have my Zynq processing system down here, and within that I have a couple of these smart connects. One is going to be for all these master connections, another one is for slave connections. That's all working well. Previous videos I have talked through how I've set up this frame buffer read, and if I go to the right with that frame buffer read, there's a video timing controller, and I also then have this AXI4 stream to video out, and that then is going to go over here to my just this custom component that I put together that just simply takes this data, RGB data, clock pixel, and converts it to native HDMI and sends out those signals accordingly. And again, if you're interested in that, you can watch previous videos on that. But I've duplicated that same thing for HDMI 2, which I have up here. So for my second HDMI output, I've got a video frame buffer read. I have a GPIO that just simply controls reset. And then I have a video timing controller, and I have this AXI4 stream to video out. I do some swapping of the color data because whatever format's coming out of here isn't exactly what I want to have for the ordering of my RGB. So I do, and actually I can check on this one, or I could open up, this is RTL, so I'd have to open up the Verilog on that. But just a little module I wrote that just pulls the right bytes into the right position and then outputs it to HDMI. So pretty similar to everything you've seen in any previous videos that I've put together where I've gone through this. And again, when it comes to my OBS capture, let me just get back to my webcam. So this over here, you're going to see this one here is this HDMI right here, and this one up here is this HDMI right here. And those are just all being driven essentially directly off of the Zynq-7000, which is what I'm running right now. But what I've added into here is this whole section up top. And really, there's not much for outputs on this. I just have it go to some LEDs on my system right now. So I have there's 3 LEDs in this little bank that I just a header I popped onto one of these so I could light up some LEDs. I'm just doing some debug output with those, but you can pretty much ignore those. And then I've added this set of stuff that I'll walk through here. So at the heart of it is this GFX controller. And this I wrote in Verilog, and it takes in a clock and a reset. It takes in a screen width and height, which I could either send in through this GPO functionality that I'll show you, or for now I just hard coded it and said, okay, the screen width I want to bring in 11 bits, and I've set that to be 1280. So 1280 by 720 is the width I'm working with on my screens. So I'm just setting that for now that way. And then I need to send into it what is the base address, basically the memory address. So when I get back, let's see if I still have this open. So when I bring back this visual here and I talk about, in HDMI2's case, this frame buffer read is reading from a certain address. Well, that's the same area of memory I want to write to from my graphics controller. So that's what I'm going to be able to pass in here, is what is that address of that memory. I'm going to ask for a command, and I support 256 commands. Right now I'm only going to use one command, which is a draw rectangle command. For the draw rectangle, I then tell it where's my X start, Y start, X end, Y end. For other commands, let's say I want to do a line, those same things will work. The X start, Y start, X end, Y end, those same params will work. If I want to do a circle, it's going to be a little bit different. Likely I'll set an X start, Y start, and a radius. So I'll add another parameter here. So that would be something I'll add for that. And when I eventually get to polygons, I suppose that's going to get quite a bit more complicated, but I will worry about that if I get that far. And then I can set a color. In the case of like rectangles and circles, I'm going to specify whether you can fill it or just have the outline. For now, I'm only supporting the complete fill, no outlines at this point. And then I've got a bit that is a start bit. And so when I have a rising edge on this is when this will actually do its processing to draw based on whatever values are on all of these inputs. And then I have a couple of these M00. This is or has to do with the AXI interface. So I am writing to DDR through an AXI interface, and that is part of this over here that I wrote. And so that I wrote as a custom component in a separate project, and I'll flip over to that and just take a quick peek at that. But what I can do is I can output what address I want to write to in memory. So what's the physical memory address I want to write to? What's the color data I want to write to it? And then there's a signal that I can basically have it rise that tells this that it needs to now go do that transaction. It needs to write that color data to that physical address. I'm controlling the reset of this over here, this graphics writer, AXI writer from my controller. I have a done signal. When it gets done drawing a shape, it flags that. I have a GPIO that can read the status and check if it's done. And then I have a couple debug signals, which are doing really nothing. You can ignore those other than toggling an LED. Every time I draw a shape, an LED toggles on my output. When it comes to the speeds of these, this one down here, this graphics writer, this is again is an AXI writer, and you can see the AXI interface over here to the right. And so that's all the signals for the AXI interface so that I can write to DDR. When I do write to DDR, it's going to use a clock speed that is my clock 1 off my processing system, which is a 200 megahertz. My controller, I'm running off of a slower clock, and that's running off of the clock 0, which in my system is a 100 megahertz. And what I mean by that is down here on my Zynq, I have two clocks set up. I have a 100 megahertz and a 200 megahertz output. And so I'm using the 200 megahertz when it comes to my AXI writing, and I'm using a 100 megahertz for the controller. And in the future, I'll experiment with speeds, but it seems like if I try to run the controller at 200, things don't work. So I'm sure that's something I can improve in the future. Now, when I do tell this, here's an address, here's a color, go ahead and initialize that transaction, write that out to memory. It does that through this master AXI interface, which if I follow that back is going to go to one of the slave connections over here on this smart connect, which is then tapped into my Zynq. So that's how I'm getting to that. And getting back up here then, when the transaction is done, there's an output of this writer that says I'm done with that transaction. And actually the way I'm setting this up, which is I'm sure far from the most efficient, is I'm doing a transaction for every pixel. So if I say I want to draw a rectangle, for every pixel in that rectangle, I'm doing a pulse out to this initialize a transaction, and I'm getting a transaction done that comes out of it. If there is an error, I also have a way to tell and check on that. There's an AXI error that I can look at. And you'll see that I also bring that error back, and I bring the transaction done back into my controller in case I want to use those. And I am using the AXI done in my controller code. If I go off to the left on this, all of these inputs that I need to bring into the controller, I'm fetching through GPIOs, and I have 3 of them over here. So I have one for specifying things like the command, the X start, the Y start. I have additional bits or bytes I need to be able to capture, like Y start, Y end, color, etc. And then I have one more that just allows me to flip a bit that says, okay, kick off, the activity on this controller when I flip something to high. So what I want to be able to then do with all of this is from C application is, set all the values in all of these GPIOs. I put together a simple little piece of Verilog that just takes the GPIO data coming in and splits it out into nice outputs that match the inputs over here. I could have just put that right in the controller, but I wanted something simple just to kind of do some traffic control. That's what this is doing. And then that comes into this graphics controller. And then I have this GPIO up here that lets me read the status. So I can tell if I start a command, I can just pull this done and see if it's actually done or if it's still drawing before I try to do something else with the graphic system. I'm sure at some point doing an interrupt will be a much better way of doing this, generating an interrupt back to my C application in PetaLinux, but I'm a ways from doing something like that. So for now, I'm going to do simple polling. And when I go back to this example here, and let me just rerun that, this is still running at a pretty good clip. So and I'm doing polling, so I'm basically saying here's a random rectangle, draw it, and then I just poll and say, well, let me know once you're done, and then once it's done, then I move on to the next rectangle. But you can see how fast it's going. That speed so far hasn't been a major issue. Let me break out of that. And I think that's about it up here. I do have this little reset sync. All it's doing is synchronizing one clock domain and its reset signal, which is coming. Basically, I want to reset the AXI writer with that, but it's in a separate clock domain. So this is just a little module Verilog piece that does that synchronization for me. And I do have an integrated logic analyzer up here, and maybe time permitting here at the end of this video, I'll talk about that real briefly, but you can ignore that for now. So if this all works, then again, I can go back to, this scenario here, and towards the end of this, I can now, from my application in PetaLinux, make a call or a series of calls to set those GPIOs correctly. And the very last one I make is this start. I raise a signal, and on the rising edge of that, the controller processes it. It actually uses this rectangle over here to generate the actual data within the memory space. So it knows what pixels need to be what values, basically what colors. And then that pixel data is written using this AXI memory writer, pixel by pixel, to the physical address of where the video buffer is. So it's doing a lot of work, but keep in mind it's running at 100 megahertz for my graphics controller, and then the AXI memory writer is running at 200. But I do have some delays coded in there, so let's just say it's running generally at 100 megahertz. That's still pretty fast. So when I tell it to draw something, I've got a couple quick GPIO commands. I have then a whole lot of pixel writing as it's working its way through the rectangle data. So if I do a 10 by 10 square, that's going to have to be 100 of these AXI memory writer calls it's going to have to make to update that video buffer. So maybe let me just open up some of the real quick, I guess the Verilog, so these here are just, IP blocks from, that come with Vivado, so from AMD Xilinx. So these are just allowing me to read from, read or write a general input, and you'll see that I'm going to read with those. So if I do come into one of these, for example, I tell it that actually these are all outputs. I'm going to programmatically write to it from PetaLinux, and then it's going to output the data over to here. Whereas this one here is a read, and it's reading the status of this done signal. So I can programmatically pull this to find out what the value of that signal is. This slave AXI interface is how I write in the values. So from my C application, I can use this write to any of these signals that it then writes out over here. But let me get back to here and just pop this back. So if I go look at my GFX controller, I know it's not going to look like a whole lot, but it took a bit to get this, put together and figured out. But what I have here essentially is I'm going to bring in an AXI clock and a reset. I've got a bunch of different signals. Again, I'm going to bring in a screen width, screen height. What is the address that I want to write this specific, shape at? And actually this here is going to be looking for the memory address, and then I'm going to have to send out an address to write. So if I know that my entire frame starts at a certain spot in memory, physical memory, I'm going to have to do calculations based on the position of the rectangle, and then that output is what I have here that'll go out to this AXI writer to actually write it to that physical memory address. I'm going to bring in a color. I'm going to have to write that color out to AXI. I do have this set up so I can maybe manipulate colors within this. So I can maybe pass in, let's say, a red and do a fade across a shape at some point. So I'm trying to add flexibility into this as I go. But here's an important signal called start. So I'm going to have to pay attention to that. When that rises, that tells me to kick off drawing this shape. Again, these are things I walk through on the block diagram. But then you can see down here, I have some internal wires and registers to track some of what I'm doing. And I'm just going to walk through this at a really high level and throw out a huge caveat. I'm learning Verilog, so I'm sure there's a lot of stuff here that you're going to say, that seems like a silly way to do it or not the right way. That very well could be, but this is what I've been able to get to work up to this point. Basically, I on a reset, I clear a bunch of these things, but then if I really look at where it starts, this is where, okay, if that rising edge of that start signal comes in, I then want to do some stuff. And what do I want to do? Basically, what you're going to see down here is I'm going to create an instance of a rectangle drawer, which is this other module that I have here. And I'm going to pass it a bunch of information, and it's going to pass back some information. And if I get over to that for a second, so I'm going to bring a lot of those same signals through, and it's going to do counting, basically. I'm going to give it a start position, in position of a rectangle, and it's going to work through that, tracking the X and the Y. I guess I do still have some things hard-coded in here. I'll be changing that later. But basically, it works through that, and it's sending out. It's basically doing the work to say, okay, I'm within a certain memory address. Here's the position of the rectangle. Here's my pixel I'm processing within the rectangle. Calculate the actual raw physical memory address, and here's the color, and output those. And so then that will be brought back into this this controller module, and the controller will now know I need to physically write to this address using this color. And in this, then I basically have that information ready, and I have to pulse. This is part of the AXI functionality, so I'm going to actually have to write to this AXI output, and to do that, I need to have the address, the raw memory address of where this pixel is going to get processed, the color of the pixel, and then I have to raise, this signal here, this AXI initialize an AXI transaction, and when I raise that out through this, that's going to allow me to kick off that write using a different IP block in here. So here's my controller, here is my address, my color, initialize AXI, and then down here you can see that this receives those three, and it's the one that's actually interfacing as a master, an AXI master. So I have to flip to a project for that, and here is that project. And two modules here. It's quite simple. On the first one, I'm basically bringing in and sending out all of your standard AXI master type of signals. So these are for my AXI master bus, and I'm going to bring in, if I want to initialize a transaction, I'm going to send out when the transaction is done. I need a clock coming in. I need to know the write address that I'm going to write to. I need to know what data I'm going to write to that address, etc. And then there's some other readies and valids and things like that. Really, all this does, for the most part, is creates an instance of this GFX writer master light. This is a really long name, but that's this here. And this has all of the input output for that master interface. And then I have just logic in here that really only supports one thing at this point, which is just simply to write, to do an AXI write. I don't support reads, although reads aren't going to be a big deal to add. Eventually I will want to be able to read so that I can maybe read a block, manipulate it, and write it back. But for now, I'm just writing a pixel. So this has basically functionality to come in here and go from an idle state to writing an address that I'm going to write to. So set the address of which memory address, and then set the data. And then if I keep coming down here, there's a little state machine that runs that. And I can get this all posted. This I started with creating a new IP, and I chose one of the AXI master projects, and then I stripped it down. There was a ton of stuff in there that I didn't need, so I just spent some time and I really cleaned it out just down to this. But at the end of the day, what this is doing is simply letting me pass in a couple pieces of information. I want to know what address am I going to write to. I want to know what color data to write there. And then I need a way to pulse or actually do the write. And then I need to be able to read the status when it's done. And then when it is done, I do have an output that tells me that that transaction was done. So these two modules give me this IP block that is nice and simple at this point. It just shows up as a block here in my block design. I can bring in my address, my color, my init transaction signal. It'll write it out to memory, and it'll come back and tell me when it's done, or indicate if there is an error. And when it is done, then I can come back to my controller and I know that it's done. So in my controller, you're going to see examples where I might say if I'm currently active in processing something and the rectangle just got done, and according to the AXI write, it finished its last pixel write, then I know that I'm done with this shape as an example. Now I do have stubbed into this that I can eventually do a circle and a line and maybe eventually a polygon. And then I'll have logic, wherever I'm using just the rectangle, to expand that out to support circles, lines, polygons, etc. What command am I going to use? Right now, the only command I support is a rectangle command. So I need to pass it in a 2 if I'm going to do a rectangle. If I pass it in a 3 for the command, I'm going to draw a circle. But this is set up in a way, I think, that it will be, extensible. So this stuff here, this idea of maybe I would add another GPO or 2 if I really need a lot of different parameters. I don't think I'm going to need a lot more. Maybe there'll be one more GPIO to support a bunch of stuff here, but those will go through this simple little splitter. That'll come into the controller. The controller then can do the actual processing of, where are each of the pixels. It can then send that data out to this writer, this AXI master, to get it updated in memory. So that probably seems like a lot, but again, as I go back to this, you can see it seems to run pretty fast as I run that. Now, beyond this, though, how do I actually, trigger all of this from PetaLinux? I do have, it's just one file here, and it looks like at the moment I'm up to 1,100 lines of code in here, but there's a lot of stuff in here, and I'm not going to say this is great code, but it's working. If I go to this, I'll go test 5 as an example. And maybe just to show you test 5 again, I'm going to start out by, I'll run test 1, which this is one of the old ones again. And the only reason I'm going to run this is it clears the screen right away. So I'm going to say for FP1, clear the screen, and it does that. Okay, so there's that drop. But now if I run test 5, it just throws up those shapes. And here's the C code that initiated that. So I just simply said, draw a rectangle on frame 0. So I've got frame 0 or frame 1, because I've got 2 frames in this memory space that I can use. And I do have a function that lets me swap frames. So I could write to frame 1 and then swap it. And that would take frame 1 and make it active, make frame 0 inactive. And then I could write on the inactive frame. And that way you don't have, I guess it reduces tearing or other mid-drawing type of artifacts you might see. I'm not doing any of that right now. I'm just writing right to the active frame. I figured, why not for now? What is the screen width, screen height? Right now, I'm not doing much with that on the programmable logic. What it would let me do at some point is some safety checks, some bounds checks, things like that. So that's future work to do. But then what is the start? So what is the start position? So in this case, I've got X start, Y start, and then I've got X end, Y end, and then color. And so I am using all of those. So where do I want to start my rectangle? Where do I want to end it? Opposite corner. And then what is my fill? Do I want to fill it or not fill it? And for now I'm saying fill because that's the only option I support currently. So I draw the first, starting at 0, 0, going to 2020, and this would be white. And so the first 2 you can kind of ignore. That's just the alpha. But then there'd be 1 byte for red, 1 byte for green, 1 byte for blue. So the 6 are my RGB. FFFFFF would be white. And that's what you see right here. Then I said go down to 3030, do a red, then go to 7070, do a green, then do a blue, and then do a red and blue, and then do a red and a green. So that's these colors you see here. And then finally a green and a blue, which is this one. And I make them incrementally larger as it draws them down. Now, if I want to go see what does one of these do, so I have a function up here called draw rectangle, and I haven't really cleaned this up. So there's probably a lot of garbage in here as I go through this. So sorry about that. I will clean this up in time and make it a little bit better code. It's pretty messy right now. But basically what I do is I say, okay, go to one of my GPIOs where I need to have the base address of my memory set and set that address. And so I want to say set the base address in there. That base address was passed in. And that base address I have set up here as 3090. So 3090.00000 is the physical address of this buffer that I'm working with in memory. And so that in this case would be this right here, this video buffer in physical memory. That's the address of it, is this 3090. So I pass in, that is where I want to do my work. And so and actually in this case, I'm saying set that GPIO 1, channel 1, there's 2 channels, and tell it that my video memory is at 3090. Then I say go to a different GPIO, set the color, because that's where I store the color, go to another one and set my X end, Y end, and whether or not I fill, and then go out and tell it what command and X start, Y start. So I'm setting up all of those parameters, and then finally I go to one of the GPIOs and I flip one of the bits that says, okay, draw it. So you've got all the data, now go ahead and draw it. So if I go to a GPIO, let's say back here, and I look at one of these, you know, I can turn on dual channel, and each channel can have up to 32 bits. So I've got 64 bits per GPIO, and these are all set as outputs. So they're going to output whatever I write to the GPIO over to this splitter. But here I'm going to say, okay, let's go write that base address, that 3090. And if I go to that definition, this is going to make it a call to something else that's just a generic GPIO write. So in it, I'm going to tell it I want to write this command, this basically graphics command base address is what I want to set. I tell it the offset, and there's a channel 1 offset, channel 2 offset. So if I'm working with channel 1 or channel 2, that's what I'm specifying here. And what value do I want to plug in? And I can go to it, and then I can see what it looks like. So I'm opening dev mem, and then I'm going to kind of come down here and look at a specific register within that. And I'm going to assign that value of that 3090.0000. And so that would have then come into this one, whichever one it was that I'm writing to, and written from my C into this to say, okay, store or put in your registers this information. Here's the address in RAM that I'm later going to want the programmable logic to be working with. But then if I back up here and I continue this process, but then I could say, okay, back to this draw rectangle. After I set the base address, I want to set the color. And so again, the color was passed in here, and in this case, the color was, you know, white. And then I'm going to jump into a call for that, setting the color, and I just tell it that I want to use this params is the GPIO that I'm using. Here's the offset. This is a 00 because it's channel 1. You know, some of these will be a channel 2. So like here's a channel 2. It's a different GPIO. And I tell it that this is the params GPIO, so it has a different address that I'm writing to, and I'm using offset 8 because it's the second channel. And then I'm going to write in a value that is my X end, Y end, and fill. So I put all that data together and write it. Really, this is just all it's doing is taking this information, where do I want to start in the rectangle and the color, and it's getting it plugged into these GPIOs. And that then will make it accessible to the controller, and then the controller can use it to actually make the call out to right to the physical memory from programmable logic. So I know that seems like, again, probably a bunch to try to track as I'm going through the video, but I'll try to get this posted if you do want to kind of walk through it. You know, all of these constants that I have up here, like what is the base address for my GFX command. So if I go back over here, here's my GFX command. How do I know its base address? I can go to the address editor, and I can find it in here, GFX command, and that's at address 4122. with 4 zeros, and there's my 4122 with 4 zeros. So that's hard coded in. Maybe I should pull that from a config file or do something else, but for now it's all hard coded. Here's the address for my params GPIO. Then there's one for my start GPIO and a status GPIO. And the status was the one over up here to read the done signal. And then I have different commands, so again, I'm getting this framework built up. For now, all I'm doing is supporting command this rectangle, so that when I do eventually get in and I say draw a rectangle, it's passing in, well, I want to do this command rectangle, and I say which command I want to set up. Well, the nice thing is, though, once I get all this done, all of these GPIO things are once and done. I have them set up. I don't need to worry about them again. Now, all I do in my code from now on is just simply say draw a rectangle. That's all I need to do. I just tell it which buffer, or which frame, sorry, within the memory, the frame 1 or frame 0 I want to write to, where and what color, and eventually whether it fills or doesn't fill. And that then gives me, again, the capability to come in here and do things like run test 6, which is just do a whole bunch of randoms. Now to do the randoms, if I break out of that, I can come over to test 6, and I have a procedure to call called generate random rectangles. And basically I grab a random width and height, between 5 and 50. I find a spot on the screen, again, random. I want it to be fit somewhere on the screen generally. I then set my start and end. I pick a color that's a random color, and then I just say draw that rectangle. And then I just repeat that. And this is just a while true, while one. Just keep doing this forever and ever. And again, that's what this output then looks like. And you can see, again, it's running through that really fast. And so if you think about how many pixels is it writing as it's doing all of that, it's moving a lot of data for this little setup that I've got. But I'm sure it's nothing compared to, for those of you that are doing live video feeds and manipulating video coming through. But I thought this is I'm happy with the results I guess I have so far on this. Now, eventually I will get to, I've got this draw rectangles, but then I can also do a draw circle. And I've started working with this a little bit. And for now, I'm just setting a center point with the start X and Y. And then I do an end X, and I just calculate the basically what is the size of the circle from that, kind of cheating, but eventually I'll have a radius that I can pass. I've got my draw rectangle, and then up here I've got to draw a line. So again, I'll be able to make the right calls, tell it that the command is a draw line command, and be able to draw a line. But that's all functionality that I need to get built out over here. You can see I've got a circle drawer and a line drawer. They don't work yet, so those are things I need to work on. Like the circle drawer actually draws a diamond instead of a circle, so that's a problem, and I got to fix that. And my line drawer doesn't work at all. So I'm not worried about those yet. I just wanted to get the first thing done, which is my rectangle drawer, which is the one that I do have connected and working at this point. Okay, so if I step back here, let's just see if we've gotten through this. I've got the test code that's writing to these GPIOs. The GPIO basically has one of the signals that I can pass on to trigger this controller to go use this rectangle to figure out the coordinates of each pixel and the color. And then that gets sent through this AXI master memory writer to the actual video buffer, which then it shows up on HDMI 2. I know at the end of the day, this draw rectangle looks probably pretty short, but it took me a fair amount of effort to really try to get this dialed in, and it's still not entirely there. I need to do some cleanup on it, but it's functional. And then the same thing on this controller. And the controller is going to get longer as I put in more functionality, I think. But then I've got these separate modules for circle, line, polygon, whatever it might be eventually. But as I add those additional pieces, this here really isn't going to change much on my diagram. I'll see more modules show up underneath the controller here, like my circle and line drawers and other types of shapes if I want to add them. But it's one consistent interface that I can go from my C application to the GPIOs to this centralized graphics controller to a writer that writes it out to memory. I think those are maybe the major things I was going to point out in the design. And if I'm missing something, throw me a note and I can try to comment on it. As I was going through this, one thing I have not spent much time getting good at yet is doing maybe some type of simulation. So I haven't done much for simulation with this. I've been kind of just writing it and testing it on the actual hardware. And to do that, I've been using this, integrated logic analyzer, which I had not used before, and pretty cool. So this is an IP block that I pulled in from Xilinx, and basically you just connect in probes. So I can connect in and say, well, I want to probe, I want to get the clock. I want to also pull in the address to write, the color to write, whether or not I'm initializing a transaction, et cetera, et cetera. So these are all the things that I wanted to pull in. Let's see, where is this one going? That would be a reset line, et cetera. So I'm pulling in all these signals. This is probably my command. Yep. And these signals here, like transaction done, I think error is probably one of them, and then this done signal also. But I connect all those up in, to their, the system is connected doing its thing. I just simply drop this in. I go in and configure it and tell it that I want to have, like in my case, 9 probes. And then I tell each probe how many port bits it has, what's the width of that probe. Is it for data or is it for a trigger? Now, once that's done, then I can actually, while my system's running, use that to put in breakpoints and kind of see what's happening with these signals. Maybe if I go back, let's do this. I will pull up my webcam for a second. That's where this box came in. Now I know there's different programmers for the Zynqs. I've got everything from a parallel one to the USB to a newer USB one to this one, which is a smart link. I had picked this up, just used online. Kind of a neat little box. So it has the connection here for JTAG, and then that connects to my JTAG header on my board. So if you've not seen my previous videos, I have a USB-C connection here for my serial connection. So USB serial, that's what like this output here is using, or this interaction. But then I also have this micro SD card. That's what I'm actually booting to. So I can go through and build all of this in PetaLinux, in Vivado, generate the bit stream, get that brought into PetaLinux, build my image, write that to the SD card, and I can boot to that SD card. And that's what I do. I kind of treat this like a little, just a little computer, and it has, the real-time clock and everything. And I persist any changes as I make them while it's running. But now I can also connect in this JTAG header through this smart link. I can connect to it either through a USB connection or a network connection, which is pretty nice. So in this case, it shows that it's on the network as this 55.152 IP. It's connected to my USB. It'll show up on my host system with this 10 dot address. And I have the firmware updated to support Vivado 2024.2. But I have this in and running, and with this connected to the appropriate JTAG, pins of my header, I can now come down and actually open up that device. And so there's the two that I've previously connected to. So I'm going to connect to, let's just say the USB one, the 10 dot. And that will open up that target. So this system is running. So, this right now, this is a live system. It's running, it's outputting, the output that I've got again, here's one of the screens, and I don't have my other screen pulled up, but let me get that pulled up. So this is the other screen that I have pulled up. This is my HDMI 1 output from earlier. So the system's, fully running at the moment. And now when I do connect to this though, I can come in and set this up to look at certain signals. So these are all of the signals for the most part that I told it to grab from my block design. So again, these signals coming into that, I can now get to right here. And I can do things like set up breakpoints. So here I have a breakpoint that says, okay, go ahead and look at this start GPIO output. So if it sees a rise, if I do start drawing a shape, it should then be able to trigger on that and show me what's happening when it tries to draw that shape. So let's see, I'm going to set this to just kind of, well, I'll just have this run once. So I'm going to hit this here that says run trigger. It tells me it's waiting for the trigger. And here's my screen. And here I'm going to go ahead and do a test 5. And that's where I just drew those shapes going diagonally from the corner. But as soon as it hit the first one of those, I can see what was happening signal-wise. So I can see that there is that signal. I told it to on start GPIO, tells me that that's 1. It went high. It went high right here, basically at the beginning. And then I can see, was there this AXI transaction? And again, for every pixel I'm writing to DDR. So for every pixel, I should see one of these little blips, on the second line. I can see the status of the DUNS. I can see what address is it writing to. So that's the beginning of this screen, is the very upper left one. There's that white box that it drew, but this is the start of it. The address is 3090.0000. And I told it to write for the data, all Fs. The command is 2, which is a rectangle. There was no error, and the reset, which is an active low, has been kept high. And then it went to the next pixel, which is 4 bytes later, because every pixel is 4 bytes, 32 bits. I've got my alpha, my R, my red, green, and blue. So those are my 4 bytes. So it went over 4 bytes to pixel number 2, pixel number 3, pixel number 4. And it's just working its way through. And I can get all the way, to the right of that, where it's done with the drawing the shape, which would be over here. And then I can see that when I got done drawing the shape, basically the done signal went high. And I can also see that there are no more of these transaction, blips happening, because it's done drawing that shape. And then this captured a little bit more until I ran out of memory. When I set this up, I can tell it how much to record, but that's the rest of the recording. And then it looks like it's getting into some other stuff. Not far enough over, though, to get into maybe the next shape, for example. But that's kind of how this works. If I wanted to, I can come in here and put in, let's see, in the trigger setup, I could tell it to also look at, tell me when it runs into blue. So I could say, well, I'm looking for a specific hex value, and let's see, red, green, blue. So FF for the alpha channel, no red, no green, and blue I want on. So tell me when that hex value is met, that now is part of this. And I think I've got that set right. Let's just see, global and, yeah, I think that's right. So if I want, I now can hit the play again on this. I can go run this from the command line again. I saw it blink back here, and I can see that at this point it's going through the same thing. It should be at a different address because I'm writing the blue box at a different location on the screen. but it's at 309E 12D0. So that's where my blue box is starting. And then let's see, actually this is red, green, blue. So that triggered, oh, it might have triggered off of the previous box. So it looks like I was at blue and now it went on to the shape after blue. So anyways, I would have to play with this and just make sure that, okay, I want to know when this is met. And I wonder even if I take this out and try it again, it's just setting up these triggers correctly. But here I got to one where, okay, it's now doing the blue, processing that blue box, and I can see that the color red, green, blue, so FF, that'd be my blue. And then I can see what addresses it's writing to. But that's where I've been using this integrated logic analyzer to do some of that debugging, just kind of check out timing of my signals, see if things are working right, not working right. Pretty neat functionality. It does take up some resources, I know, and when it gets into routing, it does slow down the routing a little bit, but that was maybe a little bit of a tangent, but that's how I've been using that as I go through doing some of this work. Maybe in closing, I'm losing my voice, so I might just hit a couple of slides here real quick. Did run into some challenges as I was going through this. Initially, I started out trying to use the test pattern generator and the video mixer that are available. And this said, this says from PetaLinux, but those are IP blocks that you would put into a block design in Vivado. And that part works fine. And, you know, I think if I went over to a bare metal using Vetus, I could get that to work, but I could not get those to work properly in PetaLinux. I could get drivers to load, but I could never get it to function. And I could not find any good resources that really show how to get this test pattern generator and a video mixer working in a configuration similar to mine. I found a couple of sites that have some information, but just when it comes to connecting all of these in PetaLinux, especially, help or information is quite limited. So I abandoned that. Initially, I was hoping that like all of this programmable logic video drawing would be on a separate layer so that I could just mix it on top of maybe just a regular frame buffer. And that way I could show it, hide it, you know, and not mess with the actual memory for the frame buffer. But that didn't pan out. Maybe I'll come back to that at a later date. I also found that as I was getting a lot of stuff into my build, the build was getting really slow. And when I say the build, I'm coming in here and I'm doing my run implementation. And between, initially I had a lot more here with the mixer and the test pattern generator. I had and maybe some other things in here like the VGA. And it was getting to the point where the resources were getting up here in total resource usage, and I was finding that I was having harder times getting timing, and that instead of a 5-minute build to get through, you know, implementation, it was taking an hour or two. So it was a drastic difference. So that's why I ended up stripping some stuff out. I took out the VGA, I took out the test pattern generator, I took out the video mixer, and now it's back to building in like 5 minutes. So that is appreciated when I'm trying to get through this. As far as the next things for me, here are some of the things I know I have ahead of me. So bug identification, you know, the stuff I have now is not perfect. It does seem to be mostly working correctly, but I need to identify any bugs as I test it, put it through its paces a bit more, fix those bugs the best I can. Tons of optimization. Again, I'm sure if you're looking at either my C code or my Verilog, you probably have all kinds of things that might pop out as things I could improve. Yeah, I'm aware of that, but step one is make it work, and that's what I've got going now. So now it's how can I make it better? Some of my C code is you know, hard set. You know, I've statically set things like the address for the memory location for the buffer. I need to make that more dynamic. I'll work on that. This, what I'm doing, should also work on my first HDMI output. So I should be able to use this to write to any of my outputs, quite honestly, the way I've done my design so far. So that's other stuff I could do. And if I make my code more dynamic and C, that should give me that flexibility. I want to have additional primitives, so I've got the rectangle working. Next, I'll probably try to get circles and lines going, and then I'll do fill, no fill for the circles and rectangles. And if I get through all that and I haven't lost patience in this process, I'll probably try to get into polygons. And when I say lost patience, it's just because this is a slow process. Every time I want to make a change in Verilog and have to rebuild, go through the implementation again, it just takes so long. So I would assume people that do this, not just for a hobby like me, but are doing it for their work, have some pretty high-end machines that can crank through that building much faster. And I think I need to get simulation set up. That's the bottom bullet I have here. Again, I've been using this integrated logic analyzer. I think getting a full simulator set up and running will be very helpful. And maybe I'll also look at being able to just do the build and then directly boot over the network and not have to write it to an SD card and flip SD cards around. Although that process is quick, that's not a big deal. I've got that all scripted and it goes fast. But it might be a bit faster if I can just boot this image off of a network and bypass the SD card. So maybe I'll look into that too. And then this Verilog generate, I believe, is the functionality that I can use to have multiple instances. So what if I want to have two processes both drawing rectangles simultaneously? I believe I can support that with this Verilog generate. So that's something that I'll look at down the road if I make it that far. This is a pretty long video, so thanks for following along. Hopefully you found this interesting. I'm sure you see things that definitely can be improved, or maybe there's a drastically different approach that I should be looking at. I would love to hear it. Regardless, my point here is just to kind of learn how to do this stuff, so I'm not so worried about is this specific result that I have right now the final destination, but more of a, okay, how did I do it? What did I learn? And how can I make it better as I go forward? But thanks for watching, and it might be a bit before I post another video again. Again, this is kind of slow moving stuff, but I want to kind of keep chunking through it. So thanks for watching all.